Well, hello everybody. I am the Heavy Metal Chemist, and I'm going to try and do some chemistry tuition videos. So, I'll apologise for using paper, a pen, and my old phone to record this, but I haven't managed to get my graphics tablet working yet. So what I want to cover today, for starters, because I'm hopefully going to do a whole bunch of things on organic reaction mechanisms, is bonding in carbon atoms and organic molecules in general, specifically orbital hybridization. So if I draw three molecules that will basically give you the idea of what we're looking at. So if we start with ethane, like so, and then we move up to ethene, like so, and then we move up to ethine, or acetylene, like so. Now what do we notice here? Well, the bonding in the carbon atoms is all different. Both of them have two carbon atoms, but they're all very, very different compounds. So in ethane, the carbon's connected to four different atoms. In ethene, it's connected to three, and in ethine, it's connected to two. Now, carbon does this because it has the fairly unique ability to bond to itself and certain other elements multiple times, so we can get single, double, triple bonds. Now, the way it does this is there are two kinds of orbital on a carbon atom, called s and p orbitals. If you've already covered this, s orbitals. This is why the periodic table looks like it is. Hydrogen has a circle, which we'll call the 1s. Carbon has a bigger one, which we'll call the 2s, and then it also has 1, 2, and then another kind of dumbbell shape, if that's going into the paper, which is called the 2p. Now, because carbon is the sixth element, what you'll notice is we fill that orbital. The 2s is lower in energy, and then we have two electrons to share between these three. And what that means is that when we want to create molecules such as these, we have to combine these four orbitals in a way that lets them stick together. And this is called orbital hybridization. So basically how this works is we just kind of mash the shapes together. So this is what's called here, that's an sp3, that is an sp2, and that is an sp. Now the way it's called like that because the s and the 3p orbitals here all mash together to give you four identical orbitals, or identical-ish anyway. Here we have 1p on its own, that forms part of the double bond, I'll come to that in a little bit, and the 2p orbitals combine with the s orbital to make three sp2 orbitals. And same here, you've got 2p orbitals making the triple bond, and two sp orbitals making the two single bonds to give it a linear shape. So how these look when you draw them out, if we have our, take that dot as the carbon core, what we end up with is, I'm not going to draw all of them, but we know orbitals have nodes like so. Basically you end up with a big node on one side and a tiny little bit on the other, and then and then that one will be coming towards us, that one will be going away from us, an old tetrahedral shape. So that has four, which is why we have a tetrahedral shape there for the sp3. sp orbitals, the carbon is trigonal planar, which means if we draw them in line with the paper, we end up with a slightly bigger bulge on the back because there's less p character in there, like so, and then we have another one there and one there, and then around here, assuming it's coming in and out of the paper, we have a p orbital that forms part of the double bond. And then for the sp hybridized carbon, So sp2. And for sp, what we have is slightly bigger bulge yet again, and I'll just draw the other half like that. And then a p orbital sticking like that, and then another one sticking like that. So basically that would form like that. So in acetylene we'd have that going to the linearity of the molecule like so. Here we'd have, for instance, H, H, and C, and then if you take methane as the example there, H, 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 H. Now these orbitals all interact in this state with the 1s orbital on the hydrogen, which provides one electron sharing to give the octet plus the 4 in the valence shell of carbon. Now if I try and draw this a bit more clearly on a fresh sheet of paper, there we go. And basically what this does is it allows us to more easily and clearly explain the chemistry of organic molecules, which will make sense when I come to do some reaction mechanism stuff, hopefully in future lectures. So if we take ethane, what we've got, we have C, C, we have our two sp3 orbitals there, they share an electron each. We have 1, 2, 3 more with hydrogen, hydrogen, hydrogen. They share an electron each, and all one comes from the hydrogen. We'll draw that in the right place. So this carbon has 2, 4, 6, 8. That's given it its full octet, and the same on that one. For our sp2 carbon in ethene, for instance, what we'll have is, I'll draw these out like that. If we imagine that these are kind of sticking in and out of the page slightly, if I draw the extra p orbitals like that, hydrogen there, 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 what we have is, we've got our hydrogen carbon bonds like so, one there, and then we have an additional 2 electrons here. And what these do is they form a cloud above and below the plane of the molecule, which gives it a nice electron-rich double bond, and this is why carbon-carbon double bonds are often called nucleophiles, or they are easily attacked by electrophiles, which are things which like electrons. Again, this will be of greater relevance in the next lecture. So, as you can see from that, that's how we get our octet. We've got 1, 2, 3, 4, 5, 6, 7, 8 coming from there, so each carbon has its full share of 8 electrons, which is how it likes it. And then if we do our acetylene now, this one's a bit trickier to draw, so carbon, draw 2 big orbitals there, 1, 2, H, H, 1, 2, so each carbon now has 4 electrons, but we also have an additional 2 electrons on each carbon. So if I draw our 2 p orbitals like so, what we basically end up with is we have a cloud there, one there, and one there. This isn't the most clear thing in the world, but we add another pair of electrons in each. So the triple bond is really, really electron rich and is quite reactive, to the point where acetylene isn't particularly stable. It has a nasty habit of polymerizing, but we'll come to that later. So basically, that's what orbital hybridization does. It allows us to explain what we observe in the shapes of molecules, organic molecules in particular, and hopefully will serve as a nice grounding for stuff I'm going to explain in the future. I just wanted to get that out of the way because it's kind of a an important thing, and another important thing to consider is how shorthand in organic chemistry is often drawn as a series of lines, etc. So if I just draw a line like that, that would represent carbon-carbon. That would represent ethane, although it's more often called C2H6 in reaction mechanisms, and representing ethene and ethine or acetylene are more commonly used because they can actually clearly represent the reactions which happen in organic chemistry. And I hope that has covered something of use to some of you. If you have any questions, do pop them in the comments thing below. Subscribe to my channel, and if you've got any ideas of any other stuff you'd like to see, please do let me know, and I'll try and do something about it. For the future, I am going to try and get my graphics tablet working and hopefully teach that way, because it's probably going to be a bit clearer than scribbling on paper, but for a starting point, I don't think this is the worst it could be. So thanks for watching. Subscribe, like, etc., etc., all the other YouTube stuff. Thank you.